like an excitation in the electromagnetic field, is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles.
So that I could speak today. Congestion in my nose, my bronchs. So
one can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles.
Let's find out what the story really says, okay? What the record shows, okay? Let's start out with some of the questions and comments that people made since last time. I had one that made me laugh a lot, and that helped
this gravitational field would be the graviton, just like an excitation in the electromagnetic field.
This fellow says the following. He says
the exchange of gravitons between two particles would result in attraction.
I said, oh, okay,
this is analogous to the way an exchange of photons
and he says this fellow, Einstein's theory of relativity,
between two oppositely charged
both
particles.
special and general relativity have been refuted by who? Dmitri Bonch.
One can attempt to treat gravity as a field.
The fellow says, unfortunately, he has no ties with anyone in science, politics, and the mass media, so cannot get his
just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles. One can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles.
Hello, can you hear me now?
One can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles.
Check the audio. Hello, can you hear me?
One can attempt to treat gravity as a field analogous to the electromagnetic field.
Well, let me turn it off, turn the whole thing off.
Gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles. One can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles. One can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles. One can attempt to treat gravity as a field analogous to the electromagnetic field.
Give me a second.
An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles. One can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles. One can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles. One can attempt to treat gravity as a field analogous to the electromagnetic field. An excitation in this gravitational field would be the graviton, just like an excitation in the electromagnetic field is the photon. The exchange of gravitons between two particles would result in attraction. This is analogous to the way an exchange of photons results in electromagnetic attraction between two oppositely charged particles.
I hope that took care of the problem. Yeah, Einstein problem is great. Okay, hopefully everything's okay now. Let me know, please, with a thumbs up or whatever. Let me start again. I had something running there. I didn't realize it. Thank you. And let me start again here. It turns out that there was a fellow who wrote a comment saying that there was a fellow who debunked Einstein, okay? And he shows me this. So the theory of relativity, both special and general relativity, have been refuted by Dmitri Bunch. And I was wondering, a bunch of what? Unfortunately, he has no ties with anyone in science, politics, and the mass media, so cannot get his work seen by many people, okay? Plus, he is poor, so he does not even have money for submitting it to a scientific journal. And then he goes on to say that this fellow discovered a new theory of economics that will solve all the world's problems. And the reason this kind of helped me cure myself because it turns out that this fellow, he wrote a book about how to get rich. And it made, to me, it was kind of funny because he says, why you are poor, how to become rich. And the first thing he says, by the way, I am poor. So this is the book he's writing now. He's going to be publishing it. Okay, so now you see what's going on with that. And I looked at his theory, okay, and it turns out that he has this theory that where he supposedly debunks Einstein, but it's not a theory. He's just attacking Einstein's equations. In other words, he says he's proposing absoluteness to relativity. You can see there what he's trying to do. And he just says that there's something wrong with his equations. And what we answer to that is equations have nothing to do with physics. Okay, we don't do equations in physics. Physics, we have to explain how this universe works. Okay, and so you can't come in with an equation and tell us how gravity works by showing us an equation. And likewise, you can't tell us with an equation whether special relativity is wrong or right, because what is special relativity? A bunch of equations. That's all it is. We look at the physical interpretations. That's the only part we look at. We will brush aside all equations. We don't care about them. We want to know what the bottom line is, what concerns physics. And what concerns physics is the physical interpretation. What is the mechanism? What is the cause? That's what concerns physics. The rest is all math, and we don't care about that. Those are descriptions. Science is about explanations. That's what theories are about. Science is not about descriptions. Okay? You can describe all you want, that's fine. When you start doing explanations, that's when you start doing physics. Okay? And so this fellow attacks the equation. We don't care about that. So it has nothing to do with physics. Another fellow says there's another great individual out there. His name is Yu, Professor Yu, and he's also apparently a dissident. He apparently destroys general relativity, and he says the following. When I look him up, it says the slide shows how our universe was created. By dynamic expansion. It was started from a low entropy state, Big Bang explosion, about 14 billion years ago, right? And he goes on and on. Well, again, the big problem here is that, they want to do equations. That's one issue. But when they get into a physical interpretation of whether the universe was created or self-created or started at some point, when time began, whatever that means, when space began, whatever that means, nothing, the creation of nothing and time, but we have a problem with all that because the physical interpretations don't make any sense. So you cannot say the universe began. And we should put that also in the context. There's like at least two versions of the Big Bang, of how the universe started. Okay, and you have to understand this because all the mathematicians are not on the same wavelength. They're not on the same page. Okay, some of them say, look, the universe started from a little ball. We're going to call that ball a singularity. Okay, it's a little dot. Okay, out there. That dot has zero volume. So if you can picture a dot with zero volume, good luck to you. Okay, that's one aspect. That's one version. The other version is that if you take all the galaxies, all the stars, all the matter in the universe, and you keep compressing it, as we go back in time, everything was closer together, according to Hubble's law, right? Everything was closer together. You get to a point, but you never get to the point. What you get is ever closer, infinitely, as they say, ever closer, but they never touch each other. All the matter never gets to touch each other. It just continues on forever, trying to get closer, and closer. So we have two versions. We have the ball version, and we have the closer and closer version. Okay? Infinitely closer version. And so we have a problem because, which one is the real Big Bang theory? And of course, these people will never clarify that for you. They will never tell you. The one group says that the other group is wrong. And so we have to decide, we can't have two versions of Big Bang. Either Big Bang was a little point that started out at some point in time, 13.8 billion years ago, whatever, right? Made by God maybe, or without God, we don't care. The point is, this point started the universe, and that's when time started, and that's when space started. It's all in there in that little point. Zero volume, zero matter, zero whatever. And then the other one is, hey, everything was just closer together 13.8 billion years ago. Yeah, but if it's closer together 13 billion years ago, that means the universe is infinite, because if you go back in time, you're just going to get closer and closer, infinitely closer, but never the matter will touch each other. Never the galaxies or whatever was there in those days, right, could touch each other. So we have a problem. We have an infinite universe, not a 13.8 billion year universe, and we have the 13.8 billion universe in the point. And you have to you have to understand that there are these two different versions, at least two, maybe there's more, right? But we have at least those two versions out there, and they contradict each other. And some mathematicians, like one's the version, the other one's like the other version. So We have a problem with that creation of the universe because they put that issue away beyond your reach. They say, well, the universe is infinite, and for that they just any question that you have, they say, well, it's infinite. That's the answer. Infinite in time, infinite in space. Well, I thought it was 13.8 billion years old, and they say, well, yeah, it is, but it ain't. And you figure it out. Okay, so that's the story today on the Big Bang. Okay, here we have another fellow, and he says the following. He says, based on the completion of more than 70% of Michelson's experiment, the following postulates can be proven. He's going to prove, okay? Light is in what? Ordered vibration of gravitational quanta. What's a quanta? I never saw a quanta. Well, a quanta is just a quantum of an amount. Okay, that's all it is. A number. And he says it's a vibration of a number, whatever that is. Okay, I've never seen a number vibrate, except in my bank accounts. They vibrate. Okay, so dominant gravitational fields adjust the speed of light in a vacuum. We are looking at, we're not looking for the ether. We will see the work of gravitational quanta. Okay, and says the result is a theory of everything. He's with this theory, he's explained everything. Yeah, and the problem is, again, if we go to quanta, whatever quanta is, quantum, an amount, that doesn't tell us anything. It doesn't tell us anything about physics. And again, all these people, they do a lot of work out there, and they want to do it through math. And they think they're geniuses, because they say, oh, look, I can put an equation here, I can put an amount for you and tell you how everything began. You can't explain how the universe began with an amount. We want to see a figure. We want to see an object, a thing out there. Then we can talk about creation of the universe in physics, for the purposes of physics. Okay? Now the fellow, he looked at what I discussed last time, 2 weeks ago now, right? And he says the following. He talks about the nebular hypothesis. He says, how does a cloud of gas do work on itself? And I suspect that this fellow is a flat earther, because it's flat earthers who have those types of questions. They don't understand gravity. And they talk about density and who knows what other nonsense. And so they have a problem because they don't understand how, gas can work on itself. In other words, how gravity can work on gases. They think gases float around, they say, because air floats around everywhere. And they say, see, like air is not affected by gravity. No gas is affected by gravity. They don't understand that they are affected by gravity. Air, gases are affected by gravity. They don't understand that because the gases float. They go against gravity. And this is where the problem is. They don't understand that. So let's make sure they understand the basics, that there is something we call gravity. It's not a something, it's a process, right? A mechanism we call gravity, okay? And here we have a fellow that I always put up there because he's, people respect authority, and this fellow has authority. He's from Berkeley, so I guess you got to respect authority if that's what you pray to. And it says, every atom on earth is pulling on every atom of you. You're also pulling on it. Let me read that again, because some people didn't hear that. Every atom on the earth is pulling on every atom of you. You're also pulling on it. So every atom is pulling on every atom. And the only way you can explain that with an elongated object, okay, you have to have something attached from one atom to another atom in order to produce that pull. In other words, just simulating here, my hand to pull on the other hand has to have some physical entity in between. You cannot do it. I cannot pull like that. Usually when I pull, this one doesn't come towards the other one. So if I pull with this one doesn't move in that direction. Okay, the only way I can get it to do it, if I have a mediator, a physical mediator, then I can pull from either end and it'll draw the other one. We can only understand pull if there's a physical mediator. These people don't understand that. And if every atom of a gas, such as air, is connected to every atom on Earth, physically connected to every atom on Earth, then we can understand why air doesn't leave the planet because it's stuck to, it's being held by all these elongated objects that are connecting every atom on Earth to that atom of air, to that atom that makes up the air, okay, oxygen. And here, let me illustrate that for you here, okay, I've shown this in the past, where you can see that here we have the air surrounding the Earth, those blue, light blue circles, going around the Earth. And those red ones, those are one atom of air that comprises the air. You can think of it as an oxygen atom, okay? It doesn't matter. So we have one oxygen atom connected to every atom on Earth. That's what those lines show. It has to be connected. Otherwise, all that air would float away and leave the Earth. And the reason it doesn't is because every atom is connected to every atom of Earth is connected to that atom, and likewise that atom is connected to every atom on Earth. Okay, so that's the only reason for the atom not leaving the Earth. Okay, so people have to try to understand that gravity even affects gases, and the gases are around here like a balloon. It floats. So does that mean a balloon? The balloon, the rubber is not made of something, because it floats in the air. A helium balloon, for example, the helium inside there and the balloon itself, they're not made of atoms, and atoms are not things, and they're not affected by gravity. Of course they are. It's just that, we have a question of density here, okay? But then, and we're not going to get into the details of that. All I'm saying is we're having atoms, they're all connected to the Earth. The balloon doesn't go to the moon. It stays at a certain level because at some point, it evens out. The pull of every elongated object that connects every atom of the balloon to the Earth, leaves it standing there. It doesn't go forever all the way to the moon. And the question is, why not? I mean, if the balloon is not affected by gravity, the moon should leave the Earth completely and go, all the way to Mars, for all we know. Okay, so here we have another fellow and talks about mass, and he says mass that is dilated, is smeared through space-time relative to an outside observer. Mass is dilated? How do you dilate a concept? And see, they talk about mass and they don't realize they're talking about a concept, and they're dilating a concept. The word dilate belongs exclusively to physics. The word mass belongs exclusively to math. So you cannot mix math with physics and say mass was dilated. That's an irrational statement. Okay, that only belongs to mathematical physics, which is an irrational religion. But you can't use that in physics, in science. Okay, and then it talks about time dilation. Again, we can't dilate time because dilate belongs to physics, time belongs to math. You cannot mix those two. It's just one aspect of dilation. It's not just time that gets dilated. Dilation perfectly explains dark matter, galaxy rotation curves. Yeah, no, it doesn't. It doesn't because you haven't explained why the dark matter, is only around the galaxy. Why is it only sitting around the galaxy? You got to explain that. I mean, why is it between the Earth and the Moon? Because if it were, then gravity would not work the same way. If we sprinkle dark matter between the Earth and the Moon, you're going to have a different gravity. And yeah, so it doesn't explain it. And again, it says the mass is all around us. No, mass cannot be all around us because mass is not a thing. You can say an ocean is all around us. You can say a lake is all around us. You can say the air is all around us, but you cannot say mass. Mass is a concept. And they say mass is all around. They talk like that. They have this irrational language. And talking about mass, here we have another fellow, and he says it's called inertia. Okay. But they also called it mass, yeah. The resistance to some external push or pull. Yeah, inertia is this resistance to being pulled or pushed, right? And the question is, that's a different definition of saying, what an object is made of, meaning all the atoms, the amount of matter in an object. The amount of matter in an object is not the same thing as the resistance to being pulled or pushed. Those are two different concepts. And so the big problem we have in math is that the word mass has many definitions. According to Wikipedia 7, in fact, I'll go that in a second. But the question is, inertia is one aspect, but inertia refers to the resistance of being pulled, and that sounds more like weight. You know, with the weights, when you put it on a scale, what happens? It causes some push against the scale, and the scale is resisting the push of this thingy that you put on the scale. And so you can't say that the weight is the same thing as mass in that case, especially if you're going to equate mass with the quantity of matter. So these are all different concepts. They lump them all together and they don't realize what they're saying, you know, and again, they get lost after a while. And the issue comes because special relativity says that, you know, when mass travels at close to the speed of light, can't travel at the speed of light because it turns into energy, etc., but if it travels close to the speed of light, then the mass increases. Well, how do you know it increases? What you're saying is that if there was a scale there and the mass, whatever that is, pushes up against the scale, it doesn't have the same mass as if it were standing still. And what they're talking about is weight. So when relativity says that mass increases, they're talking, because of speed, they're talking about weight. They're not talking about mass at all. And if you put a scale there, you're talking about the resistance the scale puts to the pressure caused by the accelerating mass. And then again, you're talking about something different. Inertia is not the same thing as mass in that sense. Not if mass is a measure of the quantity of matter. So again, we have all these definitions, and that's what's preventing all the mathematicians from making sense of mass. And finally, they say, we don't really know what mass is. You know, as John Wheeler said, you know, they have no idea what mass is. They told us what it ain't. They don't tell us what it is, okay? And that's the issue. If they can't tell us what it is, we don't care what it ain't, okay? And here you see the different definitions according to the Wikipedia. It says in mathematics, I think that's what it says, one may distinguish conceptually between at least 7 different aspects of mass, or 7 physical notions that involve the concept of mass. There are a number of ways mass can be operationally defined. And operational and functional definitions are all irrational. They come at the end of the dissertation. They don't come at the beginning. The way it works in science, you have to define first so we can follow your presentation. What these people do is say, let me run an experiment, let me do an operation, and then what will happen at the end of that will be the definition. So you need to perform an experiment to arrive at a definition. But here you can see some of the problems that they have because they have all these different definitions. They have inertial mass, active gravitational mass, passive gravitational mass, and says rest energy, curvature of space-time, a different notion altogether, and quantum mass, and they have all these different definitions. Okay, so you can look them up in the Wikipedia and you'll find all these different versions of what mass is. And yeah, we don't know what mass is because the mathematician, the guy giving the presentation, the one who's vouching for mass, has to tell you what mass is. If he cannot tell you, well, you know, I'm sorry, you know, your dissertation is over. You haven't taught us anything. We haven't learned anything from you. Okay, and so this is a big part of the problem. Okay, and finally we have another fellow, and he says the following. He says, in fantasy, not present in the material world, is fantasy and not present in the material world. Then it is part of reality. Video games are present in reality. While video games may not be natural, it does not mean they are not present. Present? Present? What do you mean a video game is present? What are you referring to? The screen? The TV set? Yeah, that is present. The video game is just a concept there, you know? I mean, what are you talking about? You're talking about what you're playing there, the images that are moving on the screen, the pixels? You know, what are we talking about? And so you have to identify the object that you're talking about before you can talk about the word real or exist, right? You know, when you go into a virtual reality world using VR headset, you know, those things that they put on their head and they can hear what they're seeing, or maybe something different, whatever. You feel the same chemical reactions of anxiety and love. Yeah, that's observation. And we don't have observers in science. We don't have witnesses in science. We don't care what you're seeing, what you're experiencing. We want to know what Mother Nature actually does. Okay? So again, what is real? Well, to know what is real, you have to define the word real. You have to define this fantastic word. And here it is. We say exist, physical presence. Okay, that's what real means because it's a synonym. And when it means first, it has to be an object. And video game, if we're referring to the game itself, the images that are going on the screen, that's not real. That's not an object. What's the real object is the pixel on the screen. That's a real object. But the game, whether you're experiencing, that's not real. We don't care about that. You can't use the word real to describe what you're feeling, what you're seeing. Okay, and this is the problem. These people mix philosophy with physics. And they think they can bring their feelings into physics and say, oh, this is what I'm feeling, this is what I'm seeing. It's real to me. Yeah, you're using the word real of ordinary speech. You're not using the word real and exist of science. In science, exists physical presence. It's got to be an object. So please identify the object before you use the word real or exist. You need to identify the object. And until you do that, you can't begin to talk. And this fellow thinks that because it's real to him, using the notion of ordinary speech, and because he feels it, he's sensing all this stuff, that to him it's real. Yeah, but for that, you need to define the word real. I'm sorry. You have to define the word real, otherwise you're going to run around in circles like all atheists, theists, and agnostics who never define the word exist, and they say, well, God exists, and the other guy says, no, God doesn't exist. And the third guy says, well, I don't know if he exists or not, I don't know what test we can run. Yeah, because they never define the word exist. It's very simple. Whether God exists or not has to do with definitions, only with definitions, not with whether you believe or not believe or know and don't know. You say, let us assume that God exists. What do you mean by that? You mean that God is a physical object first, and second, that if this God thingy, whatever it is, has distance with respect to me, that I can put a straight line of direction from me to that thing. If God looks like a human being, like the Bible says, no problem. Then there's got to be a straight line of direction from God's chest to my chest. Okay? Then God exists. He exists not because I believe or stop believing. God exists by definition. Because that's what I mean by exist. I mean that God is a physical object and he has location. Then God exists. And so we say, let us assume that God exists. Now you can explain whatever you want, because now you've justified the existence of God for the purposes of your theory. That's valid. And same goes for space-time. You can say space-time exists. Well, what do you mean by that? Is space-time an object, a thing? And if it is, hey, draw a picture of space-time. Once you do that, okay, no problem. Now, if you want space-time to exist, it has to have location. There has to be distance between my chest and space-time. Then space-time exists by definition, not because I believe or stop believing. Okay, let's go to the main course of the day, Einstein's Aether. And I'm going to start the talk with a little image that came out of this thing that they've got out there in space, and the telescope, right? And here it is. This is what I saw. It says, we now have better window than ever into the center of our galaxy, the Milky Way, and it's filled with exploded stars, magnetic streaks, and a giant black hole. And there you see the black hole somewhere in the center of our beloved galaxy, and it's quite big. You can see that the one in the center there, right? It looks more or less like the snapshot they took a couple years ago, for which they gave him the Nobel Prize, right? And except that it's not dark in the center, it's just light all around. Okay, but what I want to point out is that thing in the center, if you can see it there, right? It's not zero-dimensional. It looks like at least two-dimensional, if not three. And a black hole singularity, right, is supposed to be zero-dimensional. So what are we staring at? What is that little golden thing? Is that a Nobel Prize medal, or what is that? And how can they take a picture of something which is zero dimensional? And so that's where we start with a problem. And here, let me confirm that just in case. Here you have good old Stevie, right? And he tells us the following. He says that Eddington was angry at Chandrasekhar, who worked for Eddington, right? And Chandrasekhar was a fellow who demonstrated that black holes actually exist. And how did he prove that? He proved it mathematically, and what he showed is that it collapses to zero size, zero radius, no shape whatsoever, zero volume. Let me repeat that. Zero radius. You know what zero radius is? That means nothing, literally. Okay? So Einstein himself wrote a paper in which he claimed that stars would not shrink to what? Zero size. We got that? Zero size is zero. Don't tell me it's infinitesimally small. It's zero small. That's how small it is. It's zero. Zero size, 0 meters, 0 feet. That's zero. That means there's nothing there. Okay? So let's get it straight. All matter in a black hole, according to the theory, is crushed out of existence. The black hole singularity is completely zero, zero volume. There's nothing there. And supposedly this nothing moves stars around. Okay? And one of the things that shows is that if it's zero size, the mass is infinite, because mass divided by, nothing there, what gives you infinity? So we have infinite mass. So all black holes are infinite mass. They're all the same size, they're all the same weight, the same mass, because it's zero volume. So it doesn't matter how much mass you have. You can have a mass of 1 kilogram, it still would be infinite because it's divided by zero volume. So if it's zero volume, all black holes are the same size, the same weight, the same mass, the same everything. Okay, because they're all zero volume. And a lot of mathematicians don't even understand that. Okay, so that's the first problem. The first problem is that, there is no such thing as a black hole, because by definition, a black hole is defined as, being out of existence, zero volume. And so, what kind of picture did they take? They take a picture of a zero volume, zero size, zero shape, zero radius thing. And so the question is, what are they taking a picture of? And obviously there is something going on there that gives them some kind of a light. They take a picture of that light, then they infer that there's a black hole in that region. Okay, because that's the only explanation they have for, why stars in the vicinity or gases in the vicinity are, rattled around. They say they're rattled around because there's a black hole there. Okay, and no, black hole has nothing to do with the phenomena ascribed to black holes. Okay, but anyways, let's get to the subject matter today. Here's the summary of what I'm going to cover. First, I'm going to cover the history of the definition of ether. Okay, well, we're going to see that this ether has evolved over the centuries, and at the same time, they've reinvented the wheel every single time because they've gone over the same material. And it's like, they weren't paying attention to what the original people said or never read them, and so they reinvented the wheel constantly. 19th century ether revolution, they had the same notion of ether as the Greeks, okay? Then what happened was in the, actually the 19th century started putting some more properties into the ether, but a lot of those properties were already discussed even by the Greeks. Not in such a sophisticated way, but they did discuss these same properties. Whether it moves or not, what is it made out of, whether it's little particles, whether it moves, lots of things that they were already discussing in the days of the Greeks. By the 20th century, we have Einstein, and people say, well, Einstein destroyed the ether. Not true, and we're going to hear his own voice saying that he did not destroy the ether. He just gave it new properties, which were the same old properties that the Greeks had already discovered or debated. So Einstein didn't contribute anything. He was just trying to fit the ether within his general relativity. Then we have today, the 21st century. What do we have today? Well, relativity and quantum, they have an ether. Nothing has changed. They just called it something different, but we still have the ether in mathematical physics today. Okay, and what they did is reinvent the wheel constantly. And the issue is really that everybody proposes a different notion of what the ether is. And some people say, well, the ether is this. The other guy said, no, the ether is that. And that's the whole problem. They have different notions of the ether because they are providing different properties to the ether. What's the problem? The problem is they never pointed to the ether. They said, that's the ether. See, if you point to the ether, we all know what you're talking about. If it's a physical object. If you're going to use it as a physical object, if you're going to introduce it into physics and say that, well, light travels through the ether, or light is the vibration of the ether, anything that you say, I don't care. But if you're going to use the ether as a physical object, the first thing you got to do is point to it. And the issue there is the ether fills space, which is infinite. Therefore, you never get to ask the question, what is the ether and how far does it go, etc. They say it's infinite, and they put you away with that. And then the other issue is that whether it fills space or it is space, those are two different notions. Is ether the same thing as space? Is ether something that fills space? In which case, you got to tell me what space is and what the ether is. What are these little balls? Why is the ether? Is the ether moving? Is it static? Are we talking about sandbox here? Are we talking about something like air? What is the ether? And they never really put their finger on that. And then, again, everybody presupposes a different ether, and everybody continues this, calling this unknown an ether. That's the whole issue. Okay, so do we have an ether today? Yes, of course. You'll find out that we do, and you'll find out all the people that say that we do have an ether, but they don't say the word ether because, like one guy said out there, Laughlin, Nobel Prize, he says it's taboo to use that word. Okay, so let's start with the Greek ether. This is what the etherists originally came up with, and I think this notion of the ether came from the East, by the way, somewhere in maybe in India or China, but these people inherited it and they just developed it at least 1,000 years later. Okay, they developed it more specifically, right? Parmenides, he says, being is the same thing as the existent, equal to a body. Okay, so if you're being, then you are a body. In other words, he was talking about existence, actually, right? And not being is that which doesn't exist, the void, but motion cannot exist because void doesn't exist, and therefore if void doesn't exist, bodies have no place to move into. So Parmenides was theorized, that motion doesn't exist. That's what he concluded. He says you cannot move into that which doesn't exist, essentially. And Melissus, who was of the same school, he says, what exists is immobile. If it moved, it would move into void, but void does not exist. Again, the same notion. Okay, you cannot move into that empty region that does not exist, because if space does not exist, if vacuum does not exist, if pure nothingness does not exist, then how can you move into that which doesn't exist? That was their, space is not a box, in a sense. It's if it's an empty box, then the box itself doesn't exist, and so a dog cannot move into that box because the box doesn't exist. You can only move into that which exists. And their notion was that essentially things displace things. So when a dog moves into a certain region, it's displacing something there. Could be air, could be water, but it's displacing something. Okay, so a fish displaces water. We can all understand that. But a fish cannot displace nothing because nothing doesn't exist. That was their line of reasoning. You have Leucippus and Democritus, and they said atoms and empty space. That's all that exists. Okay, and so what is space? Well, they thought of it as vacuum, as nothingness, and they separated being from not being. Full versus empty. And where space and void says unoccupied space or place, right? So you have this region that is there that is unoccupied by an object. Okay, and they were not the majority. The majority were irrational. They were like Parmenides and Melissus. And Plato and Aristotle essentially copied Parmenides and Melissus. Plato said nothingness doesn't exist. There's no such thing as vacuum. Eventually that evolved into this quote that we have today, nature abhors a vacuum. Okay. And Aristotle, he specified exactly what the ether was, because the ether was supposed to fill all of space, right? And he came up with this notion of the corpuscular nature of ether, right? That was an air. That's why they call it ether. Ether simply means air. It's like a special kind of air, right? And he says, whatever possesses dimensionality is body. Only three-dimensionality satisfies the existence of things. Thus, empty space, vacuum, cannot exist. So this was where we started out. Okay, so just be aware, these were the notions that the Greeks bequeathed to us, about the ether and space and that world that we cannot see. In fact, air we cannot see either, and it's made out of atoms, but they didn't know that at the time, really. And so here you have the Greek ether, okay? Essentially, it was out there. You had the four elements, fire, earth, water, and air. And the ether was somewhere out there. But the problem is, with this, is that the first problem is that the ether was not here on earth. So what I showed there is not correct, okay? It's not that the ether was right over, the Parthenon. The ether was outside the earth. Okay, the ether was more like this here. Let's see if we can show this. If that's the earth right there in the center, and we have all the four elements, well, the ether was really outside of the earth. It was something that only concerned the gods, that only the gods could see or feel or whatever, right? And they looked at it really more like this. Okay, so you can see that the ether was really out there. It was beyond the reach of any rational individual. Okay, and they said, look, the ether just belongs to the gods. Don't try to understand it. So if the earth, air, water, fire, and earth itself are there in the center, the ether was there out there in the region of the gods. It was beyond rationality, beyond the reach of rationality. You can't ask the question because it's out there. Okay, run an experiment to find out if the ether is out there. And they did in the 19th century. Okay, here you see something which came out in the late 19th century, but it's a picture that they probably copied from much earlier. And it's a engraving of a fellow sticking his neck outside of the air of the earth, right? The sphere that surrounds the earth somehow. And what's outside is the ether, okay? The ether is out there somewhere. And this is more or less a notion that Aristotle had, that, the ether is really outside our experience. Okay? So they put it out there. And of course, by the time you get to the 19th century, people say, well, let's find out. Let's see if we can reason this out, if we can find out if there is an ether, because the earth is moving around the sun. Is it encountering ether? What's the story here, right? They try to figure that out. But before that, we got to the 17th century where we made the next advances with the ether, where people started asking questions. And one of the first guys to ask questions was this fellow, Descartes, René Descartes, okay? And he says, what is the ether? Well, it's a subtle matter, right? Matter that fills space and explains the absence of vacuum. Because again, he did not believe that there was anything like empty space or vacuum. He says, one object simply pushes another out of the way, or one object moves and leaves the space for another one to occupy. But there's no such thing as absolute vacuum, nothingness. And his reasoning was that nothingness cannot possess any extension. Okay, it cannot be length, right? So if God removes all matter from the universe, space vacuum would have no extension. Therefore, emptiness does not exist. That was his reasoning. There's always matter, occupying every and all regions without any space between bodies. And this is a quote from him. This stance is made of extension and therefore cannot exist without an extended substance. Okay, so distance has to be covered by a substance, meaning length. There's no such thing as distance, because distance is the separation between two objects, or like I like to say it, distance lies between lengths. Okay, and so there's no such thing as distance. Everything is length, because there's always an object there between two objects. Okay, Robert Boyle, he went in there and says, subtle matter that fills space and explains the absence of vacuum. Again, the same notion that you have this ether, this bunch of particles, and the way he looked at it, it's just a corpuscular medium. Okay, and so did Huygens, and essentially all these people had the same notion in the 17th century that it was just a bunch of particles out there. And that is essentially the same notion that I think Aristotle and Plato had and all the Greeks, that it's just a bunch of particles out there, okay, that form like a backdrop to matter. Okay, so including air. So air was within the ether, right? Not to be confused with ether, it was some kind of gas that was inside the ether. And light was something that either went through the ether, which is another issue, right? Well, it went through the ether, or was the vibration of the ether. And again, you had to figure this out, what they really meant. So Huygens said, light consists of longitudinal waves, what? Propagating through the ether. Okay? So you had this notion whether the ether was the vibration, light was the vibration of the ether, or light was something else separate from the ether that was propagating through it, through this ocean. So we were either talking about a fish moving through the ether, or we're saying that a fish is simply vibrating water. Okay, that's where the situation here. Newton had the same notion. He said subtle corpuscular elastic medium that fills space. That was his notion of the ether. Light is comprised of particles that travel what? Straight through the ether. Okay, so again, all these people had the notion that light was something different than the ether. Okay, it's going to be in the, I guess, up to the 19th century, where they're going to start saying that ether is, that light is the vibration of the ether. That's when that notion takes place. Until then, 17th and 18th century, they thought that light was something different than the ether. And the only issue was whether light was a vibration, up and down vibration through the ether. And they thought really in terms of longitudinal waves, or like Newton said, it ran straight through the ether. But it's not clear, and again, we would have to pick their brains because nobody made it clear in those days, whether the light was itself the ether, the vibration of the ether, or something where the ether itself was acting. Newton for sure thought of light as corpuscles that traveled through the ether, like if these corpuscles were different than the ether, okay? And, here we have Descartes. It's important to see his notion because he thought of ether as a bunch of vortices. And so he had this notion, and again, this is not his picture, but it's someone who illustrated what Descartes was saying, that, the earth there had all these vortices all around it. The space around it was full of all these vortices. And here is Descartes' real version. It looked more like that. Okay, you can see all these vortices, and he had this notion that the ether consisted of all these vortices. And the only question here is, where are those lines that separate one vortex from another? These vortices, they have shape. They stop at those black lines that surround them. And the question is, what are those black lines? I don't care about the vortices. I care about the black lines. What are the black lines that separate one ether from another? One vortex from another? And that's where the problem comes in. The problem comes in, these people never specify what the black lines are. I mean, is that space? What is that? What cuts one vortex from another? And this is where the whole problem is. They never addressed that. No one ever addressed that ever. They just kept saying, well, it's all these vortices. Yeah, if it's many vortices, what separates one vortex from another? What is the dividing line? That's what we need to find out. And here you can see more or less what good old Descartes had in mind. And again, you can see there are differences between the blue-violet there and the orange-yellow. You know, so if we have an orange-yellow type vortex, right, what separates it from the blue-violet? That's what you got to explain. Obviously, we can identify the separation between them. So what gives separation between, what's the dividing line? And, you know, here I kind of stopped it so that you can kind of look at it and say, okay, here you have the vortices. You can see that they're all separated one from another one. And I divided them with these white lines. Okay, so you can see that one vortex is not the same thing as another vortex. I want to know what the white lines are. That's what I want to know. And of course, they can't tell you that. They say there are all these vortices. Yeah, just tell me what the white lines are. What gives shape to each one? What separates one vortex from another? That's what we want to know. And until you can answer what the white stuff is, you can't talk about vortices, many vortices. You have to identify those white lines. And they never did. Neither did Descartes or anyone who came after. Newton, on the other hand, you know, he had this notion. He says, I don't know what the ether is. And he writes that in his optics treatise. He says, its particles are exceedingly smaller than those of air. So he knows what it is. It's a bunch of particles. Okay, that's what he's saying. So he does know what it is, but he can't draw the picture because he's going to say that it's infinite. Okay, and by saying that it's infinite, all he's doing is putting away from your questioning, from your reasoning. He's not going to answer the question. He's saying, well, it's infinite. You know, don't worry about it. That's the way they handle all that stuff. Okay, in 18th century, not much happened, but there was one fellow, Bernoulli, and he got a prize for saying the same thing that Descartes said, essentially. He says that the ether was made of all these whirlwinds, you know, these vortices again, you know, and that's more or less what he had in mind again. You know, what separates one vortex from another? And he says space is permeated by ether. Permeated, what do you mean? Is space equal to ether, or is ether something different than space? And he's suggesting that, you know, ether fills space, like if space were something else, and that would tell us what separates these vortices. What separates them is space. So you have to tell me what space is, okay? And so he goes into the ether, and he says it's made of whirlpools, it's inelastic, it enables transmissions of vibrations, and corpuscles of light travel through the ether. That's more or less his proposal. But again, he doesn't tell us what the ether is. He doesn't point to the ether. He just says, look, it's all these vortices. And what do you mean by that? What is a vortex? You know, what are we staring at? What are these colors, you know? I mean, those colors are not his, but this is probably what he imagined. And so, again, none of them pointed to the ether and says, that's the ether. They would have done that, you know, like you point to a tree or you point to a rock and say, that's a rock. We all understand that because we see the rock there, we say, okay, that's a rock. He points to the vortex, what is here? What am I staring at, you know? Just a bunch of colors? What separates one group of colors from another? What separates the yellow-orange colors from the blue-violet colors? What's the separating line? And again, they'll never answer that question, and they won't tell you if the ether is what fills space or is space. Those are two different notions. And then the question is, you know, how big is the ether? Well, it's infinite. Well, what do you mean by that? What kind of object is infinite? You know, and so all these questions have to be answered. They never answered a single one of those. They just left it out there and say, oh, you figured it out. You know, so you can't even ask that question. And so, yeah, here we have space particles. Okay, this is what I'm referring to. They say, well, the ether is all those black squares or rectangles or whatever you see there, right? And we don't care about the black stuff. We care about the white stuff. What's the white stuff that separates one square from another? And when you have a virtual particle, right, even today, right? And well, let's stop this a second. okay, you have a virtual particle come into our world, it leaves a hole behind, a hole in space. Does that space look white? I mean, you're pulling a particle out of space, the virtual particle, and the question is, does it leave a hole in space? And you would think that these people think that way because they say that, the particle comes from the void, goes back immediately before they can measure it or do anything with it, and goes back to be in space. But in that split second, in which it comes into our real world, makes itself visible or whatever, detectable, and then goes back. In that split second that it comes into our world, does it leave behind a hole in space? And so again, we need to find out, if these virtual particles, which are the modern ether, right? If a particle of that ether comes into our world, does it leave a hole behind? Or is the ether the same thing as space, meaning a single block, meaning there are no particles of ether? And what do you mean by that? I mean, does it move? This thing, is it malleable? If it's malleable, why is it malleable? Is it because, it's separated, made out of little discrete particles? All these questions have to be answered before you can talk about the ether. And they never do. They just say, oh, you know what I mean by ether. Oh, yeah, no kidding. What do you mean by ether? Please tell us. Well, by the time we get to the 19th century, you get to these notions, okay? They started putting properties or giving properties to the ether because they had to kind of reconcile them with the math, with what they were observing in the lab. And so the question was whether the ether was continuous. Was it a continuous medium, meaning made of a single piece, really? That's what continuous means in physics. Or is it made of particles? Does it fill space, or is it the same thing as space? Can the ether move in space, or is it a stationary ether? These were the issues that the 19th centuries were debating. Does the ether move? Does matter drag the ether? Called the ether drag, and whether the ether was a liquid or a solid, because they needed the solid for the propagation of waves, which according to the 19th century was a wave century. Everybody believed in the wave nature of light, and that the ether was the movement of waves. And so they said, look, if waves have to move there, especially transverse waves, the ether has to be a solid. But then on the other hand, they had to account for the ether drag, objects pulling on the ether, like the earth dragging the ether around. And for that, they needed the ether to be a liquid. And so they had these contradictions that they tried to embody within the ether, within the notion, the definition of what they meant by ether. That's where all the problems were in the 19th century. You can see the big problem they had. They had all these contradiction. They had to be a solid, it had to be a liquid at the same time. And they said, well, how can that be? It had to be, made of particles at the same time, made of a single piece. How can that be? And so on and so forth. They had all these contradictions they had to resolve. One of the first persons who started with all this nonsense was Fresnel, okay? Arago and Fresnel, both of them. Here's Arago says, in 1810, Francois Arago attempted to measure the extent to which corpuscles of light would be refracted by a glass prism at the front of a telescope. He expected that there would be a range of different angles of refraction due to the variety of different velocities of the stars and the motion of Earth at different times of the day and year. Contrary to his expectation, he found that there was no difference in refraction between stars, between times of day, or between seasons. So he had a problem there he had to resolve. And then in 1818, Fresnel examined Arago's results using a wave theory of light. He realized that even if light were transmitted as waves, the refractive index of the glass-air interface should have varied as the glass moved through the ether to strike the incoming waves at different velocities when the Earth rotated and the seasons changed. Fresnel proposed that the glass prism would carry some of the ether along with it. He was the guy who came up with the ether drag, right? If so, that the ether is in excess inside the prism. he realized that the velocity of propagation of waves depends on the density of the medium, and so proposed that the velocity of light in the prism would need to be adjusted by an amount of what? Drag. Okay, so he comes up with this notion, this amount of drag that was carried because he had to explain certain things that he was observing with a prism. Okay, and one guy who really got into that was George Stokes, who was head of the Royal Society for a while. He was a champion of the ether drag. But, ether drag had its own problems. And one of the fellows who also picked up on that was Lord Kelvin, and he took it one step further and said, hey, the ether, all those little dots there in the background, what they form is atoms. And what are atoms? Well, atoms are different configurations of the ether. Okay, so you have all these swirls, all these Descartes-like vortices, or Bernoulli whirlpools, or whatever, and each one was a different atom. So he had to explain atoms with this. And again, they had to make this thing like, the ether morphs into all these things, or the ether itself turns into atoms. Okay, so if you want to know why matter is there, well, matter is the ether in some other configuration. And what was a configuration? It was some kind of swirl, some kind of vortex. That's the notion he had in mind. He tried to make sense of it. I guess he couldn't. By the end of the century, you get to this fellow. His name is Lorentz. Okay, and Lorentz had this flexible, you could say, fixed ether, static ether, the stationary ether. And he says that we cannot speak about an absolute rest of the ether is self-evident. This expression would not even make sense. When I say for the sake of brevity that the ether would be at rest, then this only means that one part of this medium does not move against the other one, and that all perceptible motions are relative motions of the celestial bodies in relation to the ether. In other words, he's holding the ether fixed, in a sense, right? Making it stationary. And he says movement is with respect to this background, this ether that's in the background. That's what Einstein's going to challenge with his general relativity. Einstein's going to have this dynamic ether. He's going to have an ether, but it's going to be a different ether, different properties than the ones proposed by Lorentz. Okay? Says there's essentially, this is his theory. He says there's a stationary medium, right, made of countless particles also, but they never identified, they never drew it, they never illustrated this thing, known as the ether. The Earth moves through this sandbox, right? Electromagnetic waves also travel through this medium, meaning electromagnetic waves are kind of like a different thing, right? And speed of light, little c, is constant in all directions, okay? Objects contract and time dilates as they move through the ether, okay? So if you hold the ether constant, then you can say, okay, what you have is everything moves with respect to the ether. Okay, so because the ether is fixed and you're using it as a reference, as a frame of reference, fixed frame of reference. And of course, that changed quite a bit. Here you have Einstein, comes a few years later. Remember in 1916, he comes up with, really 1915, I think it was October 1915, beginning of January 1916, he comes up with general relativity equations. And because of those field equations, he's got to make sense of the ether. And he had this notion of the ether, the traditional ether of the 19th century, and he's going to change that. He says, look, the ether is really dynamic. You can't, put a stake and say, I'm going to reference my motions with respect to that stake, because the stake itself is moving. So he's saying that the ether is also in motion, and with this, he kind of debunks, or at least gained more people who voted for him, associates, people who follow him, than Lorentz. In fact, even Lorentz, I think, finally changed his mind to some degree, saying that, yeah, there is an ether, but this ether cannot be a static, a stationary one. It's got to be a dynamic one, okay? And so Einstein comes up at 1918, a couple of years later, he says, Whereas according to the special theory of relativity, a part of space without matter and without the electromagnetic field seems to be completely empty, that is to say, not characterized by any physical properties, which space obviously doesn't have, It doesn't. We cannot talk about physical properties of space, right? According to the general theory of relativity, even space that is empty in this sense has physical properties. So he starts making this space into a thingy, okay, which is what they had in the 19th century also, even today, right? That they make space into a physical object. They say it's a thing, it's a medium, it's an ocean, it's a bunch of air or whatever, right? This state of things can be easily understood by speaking about ether. So he did vouch for the ether. One must only be careful not to attribute to this ether the properties of ordinary material objects. Okay, he writes that in 1918. So he did believe in the ether. He had to put the ether in there. He couldn't get rid of the ether because he says, look, otherwise even general relativity doesn't work, because if you're going to use general relativity, you're going to put a weight on space-time, and it's going to warp space-time. Space-time had better be something, and he says it's an ether, okay? It's some kind of ether. We're not going to call it ether because it's taboo, but it's a thing, okay? We're going to push this thing down, then we can explain why the Earth doesn't fly out of the solar system, because there's a thing there that prevents it from flying out. But it's not a static one. It's a malleable one, because you can push space-time downwards. You can't just have the Earth go around a stationary ether. It's got to be flexible ether. Okay, so they made it flexible, malleable. Okay, and a couple years later, around that time, you have to remember there's a lot of politics involved here. You had the Germans, especially Philip Leonard, and Leonard hated Einstein primarily because he was Jewish, and Leonard, he was a nationalist, he was a German, he hated Jews. And he started this concept of Jewish physics as a result of Einstein, okay? So by 1919, 1920, they're talking about Jewish physics. Okay, what are they talking about? Well, remember that the war ends in 1918 with the defeat of Germany. Germany surrendered, right? And so now you have these Germans, who were coming up with all these theories about how the universe works, especially about the ether. And Leonard was completely against Einstein's theory of relativity. He dismissed that as Jewish physics. And what happens? 1919, it's Arthur Eddington, who through an expedition confirms Einstein's theory of relativity by saying, hey, light does bend around the sun. We confirm general relativity, the Jewish physics. He's not referring to a German because Einstein was German. He's not lifting Einstein because he's a German. He's lifting him because he's a Jew and because the Germans hate Einstein. The people in Germany, the people who were in the universities who were doing research, they hated Einstein. They said, hey, he's a Jew. And so we're talking about politics here. We're no longer talking about science. And they bring this subject up. And so here's a rundown of that, which is important to keep in mind for the times, because they're going to decide at this point in time what the ether is, whether there is an ether, whether it belongs to general relativity, whether we should talk about the ether at all, whether it died with the Michelson-Morley experiment. Okay, so here it is. You have first Einstein. He says 1905 to 1916, Einstein rejects the ether. During this period, he did not believe in the ether. But in 1916, after coming up with a general relativity theory of general relativity, says Einstein's new fluid malleable ether. That's what he proposed. Okay, it's an observer-based ether, right? Philip Leonard, who hated Einstein, he comes up with a different notions that general relativity simply renamed the ether as space. That's what he comes up with. And Hermann Weyl, if you want, he was pro-Einstein. He says, well, the gravitational field is ether. Even he had to admit it, and versus Newtonian absolute space. And so Einstein realized that he had to do something about his ether, his notion of the ether. He couldn't get rid of it, And he said, well, yeah, the ether exists, but it's not that static one or stationary one that Lorentz was talking about. And then by 1919, again, Arthur Eddington confirms general relativity. He's not interested really in not only the scientific part, you could say, of whether light really curves around the sun. He also wanted to bash the Germans, especially people like Leonard, by saying, hey, you know, you're this individual you're attacking, Einstein, he's our hero, because not because he's a German, but because he's a Jew. And so they get into this thing where they prop up Einstein, make him a hero, and just in great measure to overcome, you know, the attack by the German establishment, by the German, especially the scientific establishment. And then you have another guy who's a little more fanatic. His name is Johannes Stark. And he comes up eventually with the Deutsch physics in opposition to Jewish physics. And he's a prominent guy in Hitler's regime, right? And so you get this Jewish physics versus Deutsch physics. So that's what the fight was. A lot of that had to do with politics and had nothing to do with science at all, or with physics, with the understanding of how the universe works, okay? But by 1921, you can see what Einstein proposes, and he says, it is clear that in the theory of relativity, there is no place for the notion of ether, what? At rest. Okay, this is what he says, okay? At rest. He's talking about the ether, but a special type of ether, meaning at rest. Therefore, in 1905, I was of the opinion that it was no longer allowed to speak about the ether in physics. This opinion, however, was too radical, as we will see later when we discuss the general theory of relativity. It is still permissible, as before, to introduce a medium filling all space and to assume that the electromagnetic fields and matter as well are its states. But it is not permitted to attribute to this medium a state of motion at each point by analogy with ponderable matter. This ether may not be conceived as consisting of particles that can be individually, what? Tracked in time, okay? So he's not talking about a static or a stationary ether. He's talking about a dynamic ether. So if you're going to gauge your motion with respect to the ether, be aware the ether is also moving, okay? So it's a dynamic ether, and you have to factor that into your calculations. Essentially, that's what he was saying, okay? And that's the ether we have today, essentially. Nothing has changed, really, as you'll see. Okay, so at the end of the 19th century, or you can even say by the beginning of the 20th century, right? These are what they proved, or what they confirmed, you could say. Fresnel's almost stationary theory was apparently confirmed by the Fizeau experiment of 1851, who was checking the speed of light, right? You know, there's a little wheel that he had between two mountains, you know, so he had this little wheel, he had the light go through the, to one mountain, hit a mirror, and then come back to this little wheel that was spinning at a great speed. And he looked at the light coming through the separation between two of the teeth of the wheels, okay? But essentially, he was running an experiment on the speed of light and supposedly confirmed the stationary theory proposed by Fresnel. Stokes' theory, remember it was the ether drag, right, was apparently confirmed by the Michelson-Morley experiment. Then Hendrik Lorentz resolved this contradictory situation in his own ether theory, which banished any form of ether dragging. So he kind of overruled Stokes, right? But then Albert Einstein comes in with a special theory of relativity and excludes the ether as a mechanical medium. But then he introduces it again in 1916 and right after that, in which he says, well, you know, general relativity cannot live without an ether, without some kind of medium out there, because you're going to have to bend it, warp it, in order for light to, you know, curve around the sun or whatever. So you can see it was not an issue of whether the ether exists or not. It was an issue of whether what properties the ether had and whether it was the same thing as space. Okay? And what do we have today? Well, here we have a summary from this fellow, and I like it because it says it all, right? His name is Robert Laughlin. He's a Nobel Prize, Mathematics, 1998. The modern concept of the vacuum of space, right? Nothing, right? Confirmed every day by experiment is a relativistic ether, but we do not call it this because it is taboo. Right, it's a bad word. You can't mention the word ether in any paper that you submit in physics, mathematical physics. If you say, hey, the ether is still there, and you talk about the ether, your paper won't get published, period. So that's why you won't hear the word ether anymore. And here are a couple proofs, evidences we have out there. I want you to see this because they're really quite funny. Here we have Sean Carroll says, probably the biggest single misconception I come across in popular discussions of dark matter and dark energy is the accusation that these concepts are a return to the discredited idea of the ether. Aha! Yeah, everybody senses that there's something wrong there, huh? They are not. In fact, they are precisely the opposite. Okay, let's see. In the 19th century, Maxwell showed the existence of waves traveling at the speed of light. The puzzle was that waves were supposed to represent oscillations in some underlying substance, like water waves on an ocean. So what was wavy? The proposed answer was the ether. The Michelson-Morley experiment implied that the speed of light did not change as the Earth moved around through space, in apparent contradiction with the ether idea. So the ether was a theoretical idea that never found experimental support. In 1905, Einstein pointed out how to preserve the symmetries of Maxwell's equations without referring to the ether at all in the special theory of relativity. And the idea was relegated to the trash bin of scientific history. Well, obviously, Sean Carroll is very ignorant in this matter. First of all, the Michelson-Morley experiment, we don't know what it proved or what it did not prove because nobody pointed to the ether, so we have no idea what the ether is. And we're talking about a bunch of particles, and that's what the ether was until that point. What did he prove? That the Earth doesn't run against the ether, that it doesn't drag it, that it doesn't hit it, that matter is not affected by the ether. What is he trying to prove? What is it that they proved? And the other problem is that Einstein, from 1905 to 1916, did not believe in the ether. But Carroll apparently is not aware that after 1916, Einstein brought the ether right back in there, and he believed in the ether all the way to the last days of his life. So Sean Carroll is very selective in his interpretation, first of all, and second, I think he's quite ignorant because he will not be able to tell you what the ether is, what he's talking about. What does he mean that Michelson and Morley debunked the ether? And until he can tell us what the ether is and what it is that Michelson and Morley debunked, we have no idea what he's talking about. And again, he's never done any research on the subject. He's just repeating what he was taught by rote at the monastery, right? And here's another fellow, and his name is Brian Greene. He says, is the Higgs field a modern-day version of the ether? Yes and no. Like the ether, the Higgs is an invisible substance filling space. Okay, filling space completely, I guess, right? But unlike the ether, the Higgs field does not provide an absolute standard of rest, which is what Einstein was suggesting, and so aligns perfectly with special relativity. So they never answer the question, what is the ether? What are you talking about? Okay, and I like the fact that the Higgs field fills all of space, and I don't know how that can possibly be, because then you have the electromagnetic field that fills all of space. You have the muon field that fills all of space. You have all these fields that fill all of space, and the question is, how can one fill all of space and have the other one also fill all of space? Doesn't one field displace another field? It's like saying, water fills all of the ocean, and we have a certain volume for the ocean, right? And then you say, well, but there's another ocean that fills the same ocean, and another ocean that fills the same ocean, another one that fills the same ocean. Well, how can all these oceans fill the same ocean as the other guy? Doesn't one ocean displace the other ocean? And they never answer these questions. They just let it go, they just say, well, it fills all of space, and they leave it at that, and you figure it out. And so what we have today is this fellow, and his name is Albert Ash, and he illustrates the ether for you. So here it is, okay? You've seen it here for the first time, or maybe the second time. Here it is. Here it goes.
One can attempt to treat
There's your
gravity
ether
as a
and the
field
electromagnetic
analogous
field.
to the electromagnetic
And those
field.
lumps are
An
the particles
excitation
of
in this gravitational field
magnetism,
would be the
photon,
graviton,
whatever.
just like an
Here you have
excitation
matter
in the
particles.
electromagnetic
Okay,
field
here you have the
is the
graviton,
photon.
the gravitational
The
field.
exchange of
Okay, you have all
gravitons
these
between
fields.
two
They have all these
particles would
lumps,
result
which
in
are, I guess,
attraction.
gravitons.
This
right?
is analogous to the way
And
an
again, what they
exchange
do
of
is they just
photons
invent
results
all
in
these
electromagnetic attraction
particles,
between
which are
oppositely
lumps
charged
within the
particles.
ether. But this ether, which they don't call it an ether, it's just
One can
all
attempt to treat
these
gravity as a field
vibrations of what a
analogous
field,
to the
whatever a
electromagnetic
field is. What is that?
An
like?
excitation in this gravitational
you know
field
what they are.
would be
You
the
can see
graviton,
because of the lines,
just like
they're
an
all
excitation
number
in
lines.
the
That's what it is.
electromagnetic
What you're
field
seeing is the
is the
vibration
photon.
of
The
mathematical
exchange
number
of
lines,
gravitons
and it's the
between two
vibration of
particles
a number
would
line
result in
gives you that
attraction.
particle, which is
This
also
is
a number
analogous
line,
to
as
the
you can
way an
see.
exchange
And
of
all they're talking
photons
about is number lines.
results in
Okay, and so they
electromagnetic
turn these
attraction
number lines
between
into
two
physical
oppositely
objects.
charged
That's the
particles.
situation today. And so, do we still have an ether? Of course we do. To this day, mathematical physics, right? Mathematical physics does have an ether. And it's these fields. They call them fields. They don't call them ether because that would kick them out of science, out of mathematical physics, right? So they have to call them fields. And they call them fields, we're okay, we're safe. We're going to call them fields. And what's a particle? What's a vibration? A local vibration of a field, which is what you just saw. So all we have is fields, and they don't want to call them ether, but they give them properties. And the properties are the same that we had all the way to the days of the Greeks, when they asked, is there a vacuum? Is there not a vacuum? Is there an ether that fills the vacuum? Is that ether static or is it dynamic? Is the vibration of that ether light, or is light something different from the ether that passes through the ether? So all these questions were around since the days of the Greeks, and nothing has changed in the 19th century, in the 20th century, or in the 21st century. We have not gotten rid of the ether in mathematical physics. With that, I'll see you next week.